Hi, my name is Padmanabhan Pillai, or Babu for short. I am a new associate teaching professor here in the computer science department at Carnegie Mellon University. I started just recently in spring of 2025. Just a quick background on myself. I was actually an undergraduate at Carnegie Mellon back in 1996, graduated from ECE. Then I went off to Michigan to do my PhD and master's work on power-aware real-time systems design. Since then, I've worked for about 21 years in industry before starting here at Carnegie Mellon. Even while I was in industry for the last 10 years, I have been teaching or co-teaching a course at CMU, so I'm no stranger to CMU or the campus. My work has varied over the years, but a common theme is that I have a strong interest in highly interactive distributed systems. So what do we mean by this? Well, distributed systems today are everywhere. They're basically using one or more computers and networks to provide a service or solve some problem. Pretty much every application we use today is some sort of a distributed system. The lowliest application on your phone likely talks to some backend in the cloud, and therefore the whole thing is a distributed system. And we use that in interactive settings all the time. Sometimes it becomes obvious. Sometimes you click on something and you get the little spinny icon for a few seconds, and you can see that this is the effect of the distributed networking being slow. Now, if it takes a couple of seconds for your email to load, that's not a big deal. But the kind of applications I like to work on, this is not actually viable. We want very highly latency sensitive applications. So here's an example of a highly interactive application. Here we see an application that's actually being run on a wearable computer, basically a Google Glass, that's actually watching the player, first-person view, as they play a game of ping pong, analyzing where the opponent is and the ball direction, and is telling or suggesting where they might hit to maximize their chances of winning a point. So obviously, in this application, there's very, very little time for the computer to actually acquire this information, make this decision, and report back to the user in order for the user to make actually adjust their play. So here, this is something that's very latency sensitive and cannot tolerate a 1 second latency. In fact, only a few hundred milliseconds are actually possible. On top of that, the device we used is very wimpy and can't actually do this computation. So we really do require a back-end computer of some kind that needs to be communicated to over the network. So in this space, there's a lot of goals and challenges, right? We really want to do these interesting real-world applications, but these are really beyond the capability of any single device often, even big machines. The interesting stuff is very, very computationally intensive, which means it's slow. Even the fastest machines may be too slow. And often the real world input data are things like video and live video and images and sound, which are also very expensive to capture and ship. On top of that, if we want to use multiple machines, every network hop in the system adds to the latency and delay and quickly eats into our total response time budget. So we've done various works to try to help hide some of these issues. So for example, in this face application, the face recognition system is fairly slow. It cannot actually run at 30 frames a second. However, once a frame is detected, we can actually go back and tell the system that in the future, we need to track this face, and then we can actually track the face and keep it privatized or anonymized in real time at the full frame rate. The general approaches we use are often to just use multiple machines and use as much computation as we can to solve these problems, often using clusters of machines. And I've done several pieces of work in my work history in this space, including distributed runtimes for classical computer vision algorithms, as we see here, where we're detecting gestures and pointing using cameras in the ceiling. More recently, I've worked on things such as JIT-compiled Python to do array computation in a distributed form. In general, we also want to leverage proximal computing because sending data to a computer that's far away in the cloud may also be very expensive. So this is the work that we've been working with Satya and his team on cloudlets and dynamic offload. And finally, most recently, we've also been looking at how we can actually split computation between a local device, such as your phone, to get that low latency advantage of a nearby device. And then you also still leverage the more compute capabilities of a more distant offload site. Currently, we're actually applying these kinds of ideas to a variety of things, most importantly, various drone-related applications. In particular, we want to use very expensive machine learning models and LLMs to help control a drone during its mission. We also want to try to actually learn from the data being collected from the drones live as it's happening during a mission. These are things that we usually think of as offline operations, but here we want to try to learn and use this data live. Another kind of application space we're trying to apply this latency sensitive distributed systems approach is on something I like to call passive life assistance. Think of something like ADAS or advanced driver assistance in a car, where it watches what you're doing passively, but then gives you an indication that you're kind of swerving off to the side, et cetera, and helping you out when you're in a pinch. Can you imagine that for your own real life? You start walking and you say, oh, you're going the wrong way. You should be going the other way to go to your next appointment. Right? That kind of application could be potentially very useful, but it really requires both low latency and high accuracy. So these are kinds of things that we would like to try. And of course, I am a teaching faculty here. I've been teaching 15440, 640 distributed systems for the past 10 years, and still plan to continue to do so going forward. I've just started for the fall semester. We'll be teaching operating systems design and implementation, or co-teaching it for the first time. And then also the mobile and pervasive computing course, which is a higher level course here at the CS department. So if you're interested in any of these kinds of research or teaching ideas, please feel free to contact me. I would love to chat. Thank you very much.